So, a little review here. Let's start off with talking about Newton's laws. Newton's first law is the law of inertia. And it just says that objects stay still or remain in motion with a constant velocity unless acted on by a force. Okay, and inertia is measured in kilograms. Okay, so mass and inertia are essentially the same thing. All right, so what does that mean? What it means is if an object has a lot of mass, changing its current motion is more difficult, right? You probably experience this a lot or understand this. And a good illustration would be the difference between changing the motion of a badminton birdie versus the motion of a big heavy bowling ball. Okay? Should be sensible that if a badminton birdie is shooting at you at 30 meters per second, that's a lot less dangerous to you than a bowling ball firing at you at 30 meters per second, which is just over 100 kilometers per hour, right? One happens quite often when you whack a badminton birdie with the badminton racket, but if you tried to whack a bowling ball with a badminton racket, you'd have a lot of trouble changing the motion of the bowling ball. So this is inertia in a nutshell, right? The heavier it is, the more inertia it has, and the more difficult it is to change its motion. Okay? The second law is a formula talking about how we change motion. Okay? And it's just this. F equals ma. Okay? And what it basically means is that force is proportional to acceleration. In other words, applying more force to a given mass will make the acceleration higher, right? So again, just think about that. Applying more force to a given object of some mass, right, will make it accelerate at a greater rate, okay? We can do a little graph to help show this. Okay. So we might have, if we're talking about a bowling ball and a badminton birdie, we might have two relationships here. We might have that one, okay, and we might have this one. Which one of these, well, let's just call them, say, A and B, which one of these, A or B, would represent applying force to the badminton birdie? Which one of these, A or B, would represent the badminton birdie? B would, right? Small amount of force causes a fairly large acceleration, or as the force increases, the acceleration increases, but the acceleration increase is greater for a given force than it is for the other one. So this would be your birdie, it's lighter, and this would be your bowling ball. So where does mass fit into this? If this is our graph, where's mass on this little relationship here? Well, if we look at Newton's law and we solve for mass, mass should be equal to force over acceleration. So force over acceleration, there you go. It's the slope of a force acceleration graph, right? So notice, right, this slope doesn't change because the mass doesn't change. Mass is set by the object. So that makes sense that you'd have like a straight slope on here. This slope is low, so it's the one with the low mass. This slope is high, so it's the one with the high mass, okay? So Newton's three laws are not really independent, okay? They're all talking about the way that objects change their velocity as they are, as they're forced. Okay. And by the way, just in case you don't know, when we say the word force, what are we actually talking about? What is a force? What's the good? Force is just push or pull. Okay, that's a really simplified way of putting it. But in terms of things we understand, if we're pushing something or pulling it, we are applying a force to it. Okay. Um, One other thing to note here. Okay. Often you'll see a little net down here. Okay. So net means the remaining force when we've summed all of the forces acting on an object up. Okay. Let's think about what we mean by that. Okay. So just before we leave Newton's second law, here is a box sitting on a surface, right? Just sitting there. So just imagine you put a present. Let's make it a present just for fun. Drawing presents. Okay, look, here's a nice little present. Okay, sitting on a tabletop. All right. Now we know that if the tabletop weren't there, in other words, if we pushed the present to the edge of the table, it would accelerate down due to gravity, right? But yet when it's sitting on the tabletop, it's not accelerating. Okay. This might seem obvious, but it's not that gravity doesn't exist, right? Gravity is still acting. We can measure that gravity by putting something like a scale underneath there. Okay. The thing is that the tabletop is preventing that downward acceleration by providing an upward force that is equal and opposite to it. So there is no acceleration here. Okay, because the net force in this case is 0, right? The downward force plus the upward force equals 0. So when we say F equals ma, we mean the net force. Okay, there has to be a net force. So if we go to the edge of the table, right, and take this present over the edge, as soon as it's off the table, this force goes away, and we suddenly have the force of gravity accelerating this mass downwards. Okay, does that make sense? Later we'll get into why all masses accelerate downward at the same rate. And the little secret here is that gravity pulls harder on heavier things. Okay, that's the little secret there. That's why all things accelerate down at the same rate. Okay. All right, and then Newton's third law. This one seems to cause a lot of confusion. And that is that action-reaction law. And you often hear it said something like, for every force, there's an equal and opposite. Let's write that quickly. Opposite force. Okay. And for whatever reason, this seems to cause issues. But basically, it's just saying this: if I'm to push something along here, okay, if I'm applying a force in this direction, this object has to apply a force back against me in some way, okay? What it's really saying is, I can't push or pull something without touching it, right? If I touch something, or if I want to push something, I have to touch it. If I'm touching it, by the very nature of what touching is, it has to be touching me, right? The harder I push on it, the more I feel it resisting my push, right? Push your hand lightly on your tabletop, you can feel it there. Push harder, right? You can feel that it is pushing back on you. You don't necessarily grow up thinking about that sort of thing. But if you imagine, right, trying to push something without touching it, it's not possible. So it's just basically saying to apply a force, ... we've got to touch something. That's a little bit simplified, though, because you can get forces in certain scenarios without actually literally touching things. Okay, so two magnets, for instance, can repel each other or attract each other without touching. What is touching there, though, are the fields around them, force fields. And action-reaction does still apply in that scenario. But without getting too complicated and without being called out that, yes, you can apply a force without touching, okay? In fact, there's a question as to whether anything really touches, but we'll get there in a minute. To apply a force, we've got to touch something, or this is kind of like, I'm just going to put sort of. But that's a good way to kind of deal with the third law for now, okay? All right, so we're just kind of talking about what things can provide force. So there are four things. There's four fundamental forces in the universe. Okay? And we'll go from, I don't know, let's go from smallest to largest. Okay? The weakest of the four fundamental forces is that force associated with mass, and that is called gravitational force. Very weak. And you can sort of get a picture for how weak it is when you think about the fact that the entire mass of the Earth is pulling down on you right now. Okay? That might not seem like all that special, but what is counteracting that force is electromagnetic force, and the electromagnetic force between your foot and the ground is enough to counteract all the gravitational force of Earth pulling on you all at one time. Okay, we'll look at numbers in just a second. So gravitational force is a product of mass, or it is caused by masses. And all masses attract all other masses. If there were only two like atoms in the whole universe, they would be able to interact through gravitational force. It acts over infinite distances. You know the sign for infinity? It's that thing. I think because you could keep like traveling along this and you'd never get to the end of it. And this was already taken. And they mean the opposite of each other. It's kind of clever, right? It's like a twisted circle. All right, anyways, it acts over infinite distances. And it's weak. It's weak in the big scheme of things. In fact, why it's so weak compared to the other forces is still like a fairly big mystery in physics. That hasn't quite been sorted out, at least to my knowledge. Okay, let's see here. The second one, in terms of strength, is weak nuclear force. We don't really study this. It, I mean, it exists with. I don't know much about it, to be honest. It exists within atomic nuclei, and I think it's repulsive. I'm not exactly sure, and I do know it's responsible for certain types of nuclear decay. And that is related to radioactivity, and we're not going to talk too much more about that. It's not something that in our daily lives we have really the ability to measure or to deal with, especially in grade 11 physics class. We can measure gravitational force, though, fairly easily. The other one that works kind of on the scale that we're used to is electromagnetic. And it's kind of interesting. Physics is like almost a game of unification. So in olden times, when people first started talking about forces, they sort of looked at everything kind of independently. So they'd look at the force of charged electrical objects and the force of magnetism that magnets would exert on one another, and the force of gravity in different scenarios, or say the push and pull in like levers and springs and ropes and so on. But then they started to like realize that electricity and magnetism were somehow related, and it turns out that they're essentially two sides of the same coin. So where you have moving electricity, you have magnetism, and where you have changing magnetism, you have the motion of charged particles. So that's kind of an interesting thing. This is the attraction and repulsion of charged bodies / the attraction and repulsion of magnetic poles, we'll say. Okay, Um, Often people try to talk about magnets in terms of charge. It's not really correct, and it's just like it's not correct really to talk about charge in terms of poles. It's a little bit complicated. We're just going to kind of have to leave it at that. One thing I forgot to mention is gravity is always attractive, okay? Which is also kind of interesting. Like there's no such thing as repulsive gravity, at least that we know of, at least that I know of. Whereas electromagnetism is attractive or repulsive. So that's another thing that sort of separates gravity out and, you know, makes it different. In fact, these two forces are kind of unified under certain conditions. So often, if you study physics, you might hear about the electroweak force. So it turns out that number two and number three seem to be related under certain conditions in some manner. Okay, and then the last one is the strong nuclear force, and this is responsible for overcoming the repulsion within atomic nuclei. If you think about it, atomic nuclei are made of protons and neutrons. Neutrons exert no charge, so you have a ball of positive charge. You have these protons which electrically repel one another, and yet they're able to stick together in a nucleus. And this is due to this other attractive force that exists within the tiny distances found inside atomic nuclei. Okay? Okay. So all particles, as I understand it, well, all of a certain class of particles anyway, particles with mass, are subject to the strong nuclear force. Okay, not all particles react to all of the forces. For instance, particles without mass do not respond to gravity. I should be careful on that. Just never mind. I forget I said that. Neutral. Here's a better example. Neutral particles do not respond to electricity or to the electrical force. So neutrons are not attracted or repelled by electrons or protons. Okay, it's a better example. The other thing is this also acts over infinite distances. So if you have two charges somewhere apart in the universe, they can interact with each other. These only work over very small distances. Okay, so their range of influence tails off. Okay, so these are the things that can make forces. Okay, so I want to talk about one example here, and I'm just going to mention fields just really quickly. Okay, and what I mean when I say fields is actually force fields. So you always hear about like force fields on like science fiction, like watch out for the force field, but really all of these objects behave with field characteristics. So here's a good example. Let's say you have the sun and you have the earth out over here. Okay? Well, the earth is interacting with the sun via a gravitational field. So the way we look at this is we say the sun has a field which points in towards it. And we can detect this field by placing a mass anywhere around it. Okay? So what we're talking about here is the gravitational field. Let's call it G. Okay, the gravitational field of the sun will act on a mass, such as the Earth. Okay, and the Earth itself also has a G field of its own that points in towards it. And if you place mass anywhere around here, it will be attracted towards the sun as shown by these arrows. Does that make sense? If I go near the sun and I take something and I let it go, it will be accelerated towards the center of the sun via F equals ma, or if I hold it still, I'll be able to feel a weight to it as the sun pulls it towards. Just like if you stand on the earth and you take a mass, like a bowling ball, and hold it up in your hand, you can feel the earth pulling it towards the center of the earth. Okay? Well, the sun exerts a pull on earth over empty space, and we say that that is because Earth is in the sun's gravitational field. Okay? Really what's going on here sort of is that Earth and the sun have gravitational fields that interact with each other. And a field is really just an area over which these forces act. Does that make sense? Okay, now let's talk briefly about touching things. Okay, so along the same lines as the Earth, pulling on the sun or the Earth pulling on a mass, if we imagine a box on a surface like we talked about before, if we think about the force of gravity acting downwards, right? So this is like we've let something go and it's come to rest on a tabletop on Earth. Well, that gravitational field of Earth is still pulling on it, okay? But we know it's not falling, so we understand there must be some upward force. We give this upward force of a surface a name. It's just called the normal force. Okay, so normal force. What is that? That is the upward force that surfaces apply to counteract gravity. And the question then is, well, what is causing that repulsion? And while I wasn't recording, we talked about that. But let's imagine you could take like a microscope and you could aim it right at these two surfaces. So if you blew them up, you'd first of all notice that although they appear smooth without the microscope, these two surfaces are actually quite rough. And not only that, if you could really zoom in, you'd see that they're made up of atoms or molecules that have positive charge in the center and negative charge smeared around the outside of them. Okay? And we sort of view them as traveling in a circular path. It's more like just a big cloud of negative charge around these objects. Okay? And it turns out that the negative outer shells of each of these surfaces will repel each other, right? So I like to draw that as little fun lightning bolts. Just to say that the electrostatic repulsion, so the electrostatic repulsion between these atoms or molecules is what is repelling the object sitting on the surface from passing through the tabletop and, continuing on its gravitational path towards the center of the Earth. Okay? So we've got gravity pulling down on this mass, and we've got the tabletop pushing back up, preventing one object from passing through another. So this right here works via a field, right? So in this case, the negative charge repels the negative charge. We've got these fields like pushing against one another, causing repulsion. So would we consider these two objects to be, quote unquote, touching? For all practical purposes, yes, they're touching. They're touching. But if you want to get like weird, really, they're kind of not touching, because how do we define what touching is, right? If I continue to push really hard down on this, I could actually like squash these together more closely, right? If I push down on them, push down on them. And if I push down on them with like the force of, I don't know, the force found, say, inside a star, I can push them so close together that these atoms will like pass inside each other. And then weird stuff happens. You might get things like nuclear fusion happening, okay? If you can push one nucleus into another nucleus. And if you can like actually collapse the protons and neutrons together, you can create things like neutron stars or even black holes, right? Or all kinds of exotic things. So on regular, normal, everyday relationships between matter, do two things ever really touch? I don't know. It's sort of up to debate, okay? When do we decide that two objects are touching, right? It's an interesting question. If I lighten the load here, would we still say they're touching? At exactly what point does this drop to zero? So it's kind of a neat question. Not something that we really need to spend a ton of time thinking about, but it's definitely an interesting way to look at the world, I guess. A more technical way. Now let's just talk about the strengths of these before we move on. If we define the gravitational force as being 1, okay, in terms of how strong it is, okay, then we would find that the weak is 1 times 10 to the power of 25. times stronger than gravity. And then if we look at the electromagnetic force, we're going to get 1 times 10 to the power of 36 times stronger than the 1 of gravity. And the strong nuclear force is 1 times 10 to the 38. Okay? So this is kind of weird. It's odd that these forces are so astronomically larger than gravity itself. And it's one of the kind of mysteries, in physics. We sort of have the physics to talk about this. That would be like relativity. Okay, you've heard of relativity. That's relativity, kind of talks about that. And then this stuff is talked about by like quantum physics. And both work well. Okay, but quantum physics can't really describe gravity, and relativity can't really describe what happens with quantum physics. And yet, it's all part of the same universe, right? Where the things that happen at the small scale are in the same universe as the things that happen at the large scale. But there's still this divide in physics, and there's this quest for unification. How can we make this jive with this? How can we use the same set of equations to describe the entire workings of the universe? Because right now that doesn't exist. Maybe one of you will discover that one day or work on that. Who knows? Okay. Now the last little thing we're going to talk about is this concept of a free body diagram. Okay. And basically what a free body diagram is it is showing all the forces on an object with vector arrows. Okay. So here's a good example. Let's imagine we have a helicopter. I like drawing helicopters because it's like kind of easy. Okay. So there it is. There's my helicopter. Right? Kinda. And let's say that this helicopter is moving along with a velocity in this direction. Let's examine what forces must be acting on the helicopter. Okay, so it's moving at a constant level flight straight forward. All right? In other words, it is moving along as if no forces are acting on it. Am I correct with that? Constant velocity at a constant height in a straight line. Okay? An object with no forces acting on it would do the same thing. All right? So in other words, what's the net force on this object? What must it be? It's not accelerating in any direction, so the net force must be 0. But that definitely does not mean there's no forces acting on it, because it's flying. Okay, it's up in the air, and it's flying around Earth. It's in Earth's gravitational field. We must have this, right? We must have a gravitational force. So this is the first force we're drawing in our free body diagram, okay? Note, free body diagrams are drawn from the center of the object with the arrow pointing in the direction that that force is acting, okay? So why doesn't the helicopter fall out of the sky? Because it's got these guys, these rotors, right? That provide lift. So we've got F sub L, lift, right? This is force of gravity G, force L with lift. I mean, these aren't official terms. I can put whatever I want. I can put FU for force up, but I wouldn't because that sounds rude, okay? And we also are moving forward, but as we move forward through the air, if you've ever stuck your hand out the window of your car, you feel a resistance, right? So we got drag force. So let's put drag force on there. Let's call that FD. FD for drag. And the helicopter works in such a way that it also will supply a forward force, okay? Pushing against drag. Oh, I want to make it a different color. How about this? Okay? And we'll call that just FA. That is the forward force applied by your rotors, okay? So this is a free body diagram showing that there's no acceleration, because if I add all these forces tip to tail, right? Up plus down plus left plus right, I always end up right back where I started, no matter what order I do it in, right? Up, drag, gravity, accel. I always end up back where I started. So F net is 0, okay? Notice how I'm adding vectors tip to tail. When I look for finding a net force, I add them tip to tail. In this case, no net force. But let's say the helicopter wants to go faster. How would it manipulate this in order to go faster, do you think? It can't reduce drag, right? It would have to change its shape to do so. So it probably increases its forward force by turning up its engines or changing the pitch of its blades, right? And so in other words, it's going to accelerate forward for a little while. But as it does so, drag will slowly increase until it's now moving at a higher forward constant velocity. Let's say the helicopter wants to move down towards the ground. How would it do it? Probably it would shrink its lift, right? If you shorten lift, now gravity is larger and the helicopter will accelerate downward. Does that make sense? Okay, so this is a free body diagram. If an object is moving constantly with a constant velocity, in other words, it's not accelerating, that must mean the sum of all of these vector arrows for force have to equal 0. If it's accelerating forward, say, then there must be a net force in the forward direction. If it's accelerating, if it's accelerating in this direction, it must have a net force in the rearward direction against its travel. Okay, are there any questions about that? Okay, let's do one more free body diagram. Let's imagine that we just have an object and we're dropping it. Say we're up on top of a cliff. We just let it go. What kind of forces will be acting on that object? Yes, at first, pretty much just gravity, right? But as the object falls and moves faster and faster, does it continue to accelerate? Can the gravity get larger on the object? No, right? That's just based on its mass. But as it moves through the air will start to provide resistance. So what you'll get is you'll get a growing drag force on this. And eventually, if you keep falling, say the ground wasn't actually there, if you keep falling, the object will stop accelerating when that drag force, when it gets to a speed such that that drag force is exactly equal and opposite to gravity. What's the name for that when an object is falling as fast as it can through air? Well, yeah, it's kind of free fall, but this is what parachutists talk about when they jump out. They accelerate, they get faster, 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 and they do their free fall, but they stop accelerating. Okay? When the drag force gets as large as gravity, they stop accelerating, right? Because at this point, F net equals 0. There's no acceleration anymore. The name for that is terminal velocity. You ever heard of that term before? As fast as you can fall through air. Okay? And we're going to leave it at that.